Hello science enthusiasts! Welcome back to the channel. Have you ever felt the ground tremble beneath your feet? That sudden, powerful jolt that makes your heart race? It's a phenomenon as ancient as our planet itself, a raw demonstration of the immense forces at work beneath our very feet. Today, we're diving deep into the world of earthquakes, exploring the science that makes our Earth shake, the history of its most devastating events, the ingenious inventions helping us understand them, and what the future holds in this seismic journey. So, what exactly causes an earthquake? It all starts with our Earth's incredible structure. Our planet isn't a solid sphere. Its outermost layer, the lithosphere, is broken into massive, interlocking pieces called tectonic plates. Think of them like giant puzzle pieces constantly, slowly, grinding against each other. These plates are always on the move, driven by convection currents in the Earth's molten mantle. When these plates interact, they do so in three main ways. Convergent boundaries, where plates collide, often leading to one sliding beneath the other, a process called subduction. This can create powerful quakes and even volcanoes. Divergent boundaries, where plates pull apart, allowing new crust to form, often at mid-oceanic ridges. Here, earthquakes are generally less intense. Transform boundaries, where plates slide horizontally past each other. This is where most of the shaking we feel originates, as immense stress builds up along these fault lines. Imagine trying to push two rough surfaces past each other. They'll snag, resist, and then suddenly slip. That's essentially what happens along a fault line. As tectonic plates move, they create immense stress on the rocks at their boundaries. Rocks aren't infinitely strong. They can only withstand so much. When the stress becomes too great, the rocks suddenly break and slip, releasing a tremendous amount of energy in the form of seismic waves. These seismic waves travel through the Earth, causing the ground to shake. We have two main types: P waves, primary waves. These are like sound waves, compressing and expanding the ground. They're the fastest and arrive first, often felt as a gentle jolt. S waves, secondary waves. These move the ground side to side or up and down. They're slower but cause much more damage. The point where the earthquake originates underground is called the hypocenter, and the point directly above it on the Earth's surface is the epicenter. The deeper the hypocenter, generally the less intense the shaking at the surface. Throughout history, earthquakes have shaped landscapes and left indelible marks on human civilization. They remind us of the raw power of our planet. Let's look at some of the most tragic events that highlight this destructive force. One of the deadliest earthquakes in recorded history struck Shaanxi, China, in 1556. It's estimated to have killed over 100,000 people, largely due to the collapse of homes built into lush cliffs. The sheer scale of loss underscores how vulnerable early societies were to such events. Fast forward to 1755, and the devastating Lisbon earthquake, followed by a tsunami and fires, virtually destroyed the city. This event profoundly influenced Enlightenment thinkers and spurred the earliest scientific investigations into seismic phenomena, shifting away from purely supernatural explanations. In the 20th century, the 1906 San Francisco earthquake became a landmark event. While the earthquake itself was powerful, the subsequent fires, fueled by ruptured gas lines, caused even more widespread destruction. This event spurred significant advancements in seismic engineering and urban planning.
Preliminary
More recently, the 2004 Indian Ocean earthquake and tsunami was a catastrophic reminder of how underwater earthquakes can trigger secondary disasters. This magnitude 9.1 quake generated a series of colossal tsunamis that claimed hundreds of thousands of lives across 14 countries, forever changing global disaster preparedness. And who can forget the 2010 Haiti earthquake, which tragically killed over 200,000 people due to poor infrastructure, or the 2011 Tohoku earthquake and tsunami in Japan, a magnitude 9.0 event that caused immense damage and led to the Fukushima nuclear disaster, showcasing the complex interplay of natural hazards and human infrastructure. From fear and superstition, humanity has moved towards understanding, largely thanks to incredible scientific inventions. The earliest known seismic instrument dates back to 132 AD in China, invented by Zhang Heng. His ingenious seismoscope could detect the direction of an earthquake using falling balls from dragon mouths into toad mouths, a remarkable feat for its time. Fast forward centuries, and the development of the seismograph revolutionized our ability to study earthquakes. Modern seismographs are incredibly sensitive instruments that continuously record ground motion, allowing scientists to pinpoint an earthquake's location, depth, and magnitude. The Richter scale, developed by Charles Richter in 1935, quantifies the magnitude of an earthquake based on the amplitude of seismic waves. Each whole number increase on the Richter scale represents a 10-fold increase in the measured amplitude and roughly 32 times more energy released. Today, while still widely understood, seismologists often use the moment magnitude scale for more accurate measurements of large earthquakes. Beyond just measuring quakes, we've developed tools to monitor tectonic plate movement and crustal deformation. GPS technology allows us to measure tiny shifts in the Earth's surface with incredible precision. Strain meters and tilt meters embedded in the ground help us detect the subtle deformation of rocks as stress builds up along fault lines. Perhaps one of the most vital modern advancements is the development of earthquake early warning systems. These systems utilize networks of seismometers to detect the fast-traveling P waves. While S waves cause most of the damage, P waves provide a crucial head start, sometimes seconds, sometimes tens of seconds, before the destructive S waves arrive. This precious time can be used to send alerts, automatically shut down critical infrastructure, and allow people to drop, cover, and hold on. So, what does the future hold for our relationship with earthquakes? Can we predict them? And how can we better protect ourselves? The holy grail of seismology is accurate earthquake prediction, knowing exactly when, where, and how big an earthquake will be. Unfortunately, we are not there yet. Earthquakes are incredibly complex natural phenomena. The processes leading up to them involve intricate interactions within the Earth's crust that are difficult to monitor and understand fully. However, scientific research continues. Scientists are exploring various potential precursors, from changes in groundwater levels and gas emissions to subtle electromagnetic signals. The advent of artificial intelligence and machine learning is also opening new avenues, allowing researchers to analyze vast datasets of seismic activity for subtle patterns that might indicate increased risk. While precise prediction remains elusive, our ability to mitigate the impact of earthquakes is constantly improving. This is where engineering comes in. Earthquake-resistant building codes. Modern structures in seismic zones are designed to withstand significant shaking. Base isolation. Buildings are literally isolated from the ground using flexible bearings, allowing the ground to move without transferring all that motion to the structure. Damping systems, like shock absorbers in a car, these devices absorb seismic energy, reducing a building's sway. Flexible materials. New materials are being developed that can deform without breaking, better absorbing the stresses of an earthquake. Beyond engineering, public education and preparedness are paramount. Knowing what to do during an earthquake, drop, cover, and hold on, and having emergency kits ready can save lives. Communities are also developing more robust early warning systems and evacuation plans. The future of earthquakes isn't about stopping them. That's impossible. It's about building a more resilient world where we can live with these powerful natural events, minimizing their impact through scientific understanding, technological innovation, and collective preparedness. From the slow dance of tectonic plates to the sudden, violent release of energy, earthquakes are a testament to our dynamic planet. We've journeyed through the science of why they happen, witnessed the devastating toll they can take, celebrated the scientific ingenuity that helps us understand them, and looked ahead to a future of greater resilience. For those of us living in earthquake-prone regions, like the infamous Ring of Fire, understanding earthquakes isn't just academic, it's crucial for our safety and well-being. Remember, knowledge is power. By understanding the Earth's shaking secrets, we can better prepare ourselves and our communities for whatever our dynamic planet throws our way. If you found this exploration of earthquakes fascinating, please hit that like button and subscribe to our channel for more educational content on the wonders and forces of our world. And let us know in the comments, what natural phenomenon would you like us to explore next?